Good afternoon, everybody, and welcome to this week's Mastering with Miss G video. And today we're going to start part 1 of Mastering Buffer Calculations with Miss G. Part 2 of this series, very short series, will follow next week. And the reason why I've chosen to focus on buffer calculations for these two videos is because lots of you will be coming on to having a look at the acids and bases topic in school at the moment, for those of you in year 13, if you haven't already started it. And buffers are the part of this topic in particular where lots of students struggle. Just the mention of the word buffers is enough to make some students weep. I am joking, but buffers are not very well liked by lots of students. So I decided that now would be a really perfect time to release some videos on how we can master buffer calculations. So we're going to need to know what we actually mean when I say the word buffer. And the two parts that we're going to look at, part 1 is how we prepare the buffer solution, and then part 2, coming next week, will be looking at what happens when we then add acid, alkali or water to a buffer solution. And when we know what a buffer solution does, which is it's a solution that maintains its pH when small amounts of acid, alkali or water are added, what we will find in next week's video is we will be doing the skills from today's video in part A to prepare a buffer and work out what its pH is. And then next week we'll have a look at how do we then show that when we add a small amount of an acid, an alkali or water to that buffer, that its pH will stay constant. And we say it stays constant, it will change a very small amount, as I've written there on the screen. It will vary within about 0.01 or 0.02 pH units, but we're going to say that that is the buffer maintaining its pH. Now it can only do that when very small amounts of acid, alkali or water are added, but it can do it. So part 1 today we're going to focus on what is an acidic buffer and how do we prepare an acidic buffer, and then how do we work out the pH of the acidic buffer that we have prepared. In next week's video, we'll have a look at what then happens when we add the acid, the alkali or the water to said acidic buffer. So to be a buffer, we have to have a weak acid and the salt of the weak acid present in our solution. And throughout this video, I'm going to use orange as the colour for my weak acid, and I'm going to use green as the colour for the salt of the weak acid. And you have to have both of those things. You can't have one or the other only, and there can't be anything else in the solution either. And when we have these two things together, as I've already said, the solution is able to maintain its pH. And the reason why it can do that is because the ratio of the weak acid and the salt of the weak acid stays almost constant, even when we add that small amount of acid, alkali or water. Because of that, the concentration of H plus ions stays almost the same, and thus the pH of the solution is maintained. Like I say, there will be a very slight variation in the pH that we calculate, but we're going to say that the pH is maintained. So in our buffer solution calculations, we're going to be using the Ka expression, and you'll be used to seeing this from your work with weak acids, hopefully. So when we write our Ka expression, we have the products of the dissociation of the weak acid on the top, and then we have the concentration of the weak acid, Ha, on the bottom. Now, when having a look at weak acids on their own, the A- came solely from the dissociation of the weak acid, and we simplified this expression somewhat by saying that the concentration of H plus and the concentration of A- would always be the same from the weak acid dissociation. So instead on the top we wrote it as H plus squared, and that made rearranging that expression and calculating H plus and thus the pH of the weak acid a lot more straightforward. But we can't say that now that we're dealing with buffers, because the A- is coming from the salt of the weak acid now that we are adding in addition to the weak acid. So the H plus and the A minus on the top of my Ka expression are not the same anymore. So if I have information about Ka, the weak acid, and the salt of the weak acid, I would then need to rearrange this Ka expression to get H plus as the subject of that expression. And that's what I've done on the second line there. So to work out the H plus concentration, we're going to need to do Ka times by the concentration of the weak acid, Ha, and then divide that through by the concentration of the salt of the weak acid, the A minus. Now, one of the things that they may do in these questions, like you will have seen when you had a look at weak acids, was they may not give you a Ka value, they may give you a pKa value. So we need to know how we can change between pKa and Ka, and that relationship is the same as pH and the H plus concentration. So pKa would be equal to minus log base 10 of Ka, and thus Ka is equal to 10 to the power of minus pKa. So it may be that as part of the steps of our method, we need to convert between pKa and Ka, and that would be how we do that. But I'm going to take this one step further. Now, this may not be something that you get taught by the teachers at your school or college, but this is definitely something that makes these buffer calculations much easier. I always do this personally myself, and I've never had any problems doing this method. What I do is, instead of using the concentration of Ha, the weak acid, and the concentration of the A minus, the salt, I just use values for the moles of those two substances. Now, this works if we think about it, because if we're working out the concentration of Ha, we do that by doing moles divided by volume, and same for the A minus concentration, it would be moles divided by volume. Those two volumes would be the same because they're in the same vessel, so therefore those volumes would cancel from the top and bottom of my fraction and would thus leave me only with the moles. Therefore, I can just sub the mole values in to there instead of having to work out concentrations. Now that makes things much easier, because if we are adding the weak acid and the salt of the weak acid into a vessel together, the volume of one will then dilute the concentration of the other, and vice versa. So then we'd have to work out new concentrations of both, whereas actually we can just work out the moles of each one we have and then sub those numbers in. Now, of course, if you are using the moles, you do need to make sure that you drop the square brackets, because when we are dealing with concentration in chemistry, that's what the square brackets are denoting. So if we're not going to use concentrations, the square brackets can't be there. But what I would always recommend is that you start by writing your Ka expression as normal, as I have done on the top. Then when you rearrange it, then if you're going to use moles, drop the brackets. And I would strongly suggest you use the moles. Once we've worked out our H plus concentration, we can work out pH. pH is always minus log base 10 of the H plus concentration, as is the case for all the calculations in acids and bases. So there are two ways we can prepare an acidic buffer. Now remember, the acidic buffer has to have the salt of the weak acid present, and it has to have the weak acid present. Now, the easiest way to prepare an acidic buffer is to just take an amount of salt of the weak acid and an amount of the weak acid and put them together. Work out the moles of what we've got of each, and then do the calculation I've outlined above. And I'm going to show you two questions that use that particular method to prepare an acidic buffer, and we'll go through working out the moles of each, rearranging the Ka expression, subbing the numbers in, and getting a value for the pH there. And that is by far and away the easiest of the two methods. The second method is that we start with an excess of the weak acid, we add an alkali, the alkali and the weak acid react together to make the salt in situ. The alkali then all has to be used up, because that can't be left over at the end, otherwise again it wouldn't be a buffer. So the alkali has to all get used up, and we have to use an excess of the weak acid, because again we need that to be present after the neutralization step has occurred. So we're going to have to work out how much alkali we've added, how much of the weak acid that's going to use up, how much of the salt that's going to prepare, but then that would then give us the moles of those two things, and then again we can rearrange our Ka expression, get a value for the H plus concentration, and then get a pH. And I'll talk you through a question that gives us information to follow that method as well. And that's what we're going to go on to now, and hopefully by seeing me do these three methods, seeing how I lay out the information, following those steps that I've put there, you will see that buffer calculations don't need to be so bad. You don't need to cry when someone says to you, we're going to do some buffer calculations, because once you know how to do them, the approach will always be either method 1 or method 2. And if you know how to do method 1 and method 2, then you'll be absolutely fine. Now, in both of those cases, those are the steps we're going to be doing. We're going to be finding the moles of the salt, finding the moles of the weak acid, rearranging the Ka expression to make the concentration of H plus the subject, subbing in the mole values and the value for Ka, which remember we may need to find from pKa first, and then once we've got the H plus concentration, we're going to get the pH. So let's have a go at doing some of these together, and then hopefully you'll be able to use my methodologies and the way I lay out my questions to have a go at some yourself. Okay, so we're going to have a look at the question that's on the screen there now. So this is following method 1, where we are adding straight away together the salt of the weak acid and the weak acid. So the first thing I'm going to do is just read through the question, and then we're going to highlight the key information that we have been told. And then from there, we're going to follow through those steps that I just worked through. So a buffer solution was prepared by dissolving 0.012 moles of sodium ethanoate in 100 centimetres cubed of 0.0520 mole per decimetre cubed of ethanoic acid. The dissociation constant Ka for ethanoic acid is 1.74 times 10 to the minus 5 moles dm to the minus 3. We've been asked to calculate the pH of this buffer solution. So the salt of the weak acid is the sodium ethanoate. So when we take ethanoic acid and it loses its H+, we're left with the ethanoate ion, which is the CH3COO minus ion. And then when sodium goes on the end of there, that then becomes sodium ethanoate, and that is our salt of our weak acid. Now we can see, hopefully, that we've already been given the moles of this. So we're not going to have to do anything in order to work out the moles of the salt, because they've just been straight up given to us in the question, which is very kind. But we are going to have to work out the moles of the weak acid, because what we've been told is that we have 100 centimetres cubed of a 0.0520 mole per decimetre cubed concentration of the ethanoic acid. But that's very easy for us to get the moles, because we can just do concentration times volume, remembering our volume obviously will need to be converted to decimeters cubed. And then we've been given a value for Ka, so we don't need to convert it from pKa, so that's nice, for the ethanoic acid, and the value we've been given there is 1.74 times 10 to the minus 5 mole per decimeter cubed. So the first thing in my list of things to do was find the moles of the salt. Now we've already been given that, but I like to have everything written down that I may need in order to answer the question in my working out space. So I've just rewritten that there. And then I'm going to work out the moles of the weak acid by doing concentration 0.0520 times volume, which is 100 centimetres cubed, which I then need to divide by 1,000 to put it into decimetres cubed. So that's then going to be times 0.1. And then I just need to work out what that is. .0052. Then I've got my value for Ka. So then the first thing that I would do if this was in my exam would be I'd write my Ka expression. So Ka is going to be equal to the concentration of H plus times the concentration of A minus, which is the salt, divided by the concentration of HA, which is my weak acid. And even though we're not going to be using concentrations, remember when you first write out the Ka expression, always write it that way with the square brackets in place. Then I'm going to rearrange this to make the concentration of H plus the subject, and at this point I'm going to drop my square brackets because we're going to be using the moles. So I'm going to do Ka times the moles of the weak acid divided by the moles of the salt. And then I can just sub my numbers in. So the concentration of H plus is going to be equal to the value for Ka, which is 1.74 times 10 to the minus 5, times the moles of the weak acid, which is, my apologies, 0.0052. And then we're going to divide that by the moles of the salt, which we were given straight away as 0.012. Then I just need to put all of that into my calculator, and that will give me the H plus concentration. So just bear with me a second while I do that. So that gets me 7.54 times 10 to the minus 6 moles per decimeter cubed. And then from there, pH is equal to minus log base 10 of the hydrogen ion concentration, and therefore the pH is equal to 5.12. And pH values should always be given to 2 decimal places, so the actual answer was 5.1226, so then I've rounded that to 5.12 to my 2 decimal places, and that's it. That is the pH of our buffer solution. I don't think that is massively difficult, and of course remember this is part 1 in the 2-part series, so that would be part A of your question to work out the pH of the buffer, and then in the second part of the question it would say something along the lines of, we're now going to add a small amount of acid to this buffer, or we're now going to add a small amount of alkali to this buffer, calculate the new pH. And what you would find is when you did that, the pH would either stay at 5.12 exactly, or it would vary ever so slightly. It might be 5.10, 5.11, 5.13, 5.14. Probably not much further outside of that range, but that would be us saying that the pH of the buffer solution has been maintained, and that would be what you would do in part B. Which isn't necessarily harder, it's just going to utilise different skills. We're going to bring in a bit of equilibria, but as a part A, I think that is a fairly nice set of marks to be able to pick up, because you're probably looking at 4 marks for that question, possibly 5. So good marks if you know what you're doing. Let's do another example. And in the next example, it's going to be still a method 1 calculation where we're adding the salt of the weak acid to the weak acid without having to make the salt first. And in this one, it is slightly harder because we haven't been given a Ka value, we've been given a pKa value, and from that we're going to have to get Ka. So there's going to be an extra mark available for this next question as a result of that, but ultimately this next question will be identical to this one. So I'm actually going to leave the question we've just done on the screen at the same time as doing this one so you can see how similar they are. So let's read it through and let's do our highlighting first of all. So a buffer is prepared by mixing 50 centimetres cubed of a 0.417 mole per decimetre cubed solution of a salt of a weak acid, NaX, with 150 centimetres cubed of a 0.0204 mole per decimetre cubed solution of the weak acid, HX. The pKa for HX is 5.12 at 25 degrees. Calculate the pH of this buffer solution. So they haven't actually given us the full names of either the weak acid or the salt of the weak acid, but they've told us that the salt of the weak acid is NaX, and they've told us that we're going to be mixing 50 centimetres cubed of that, and the solution has a concentration of 0.417. So we can work out again the moles of that really easily because we've got a volume and a concentration. And then again for the weak acid, which is HX, we are adding 150 centimetres cubed of that solution, and the concentration is 0.0204. So again, we can work out the moles of the weak acid really easily. We do have to work out a value for Ka this time because we've been given a value of pKa, but we can do that, and I'll make sure I outline how to do that. And then again, the ultimate goal is calculating the pH of the buffer solution. So starting with the salt again, the moles is going to be equal to concentration times volume, so 0.417 times 50 centimetres cubed, which I need to convert into decimetres cubed, so 0.05, and that will then give me the moles of the salt of the weak acid, which is 0.02085. And then we can do the same thing for the moles of the weak acid. So we've got a concentration of 0.0204 and a volume in decimetres cubed of 0.150. Which gives me 0.00306 for the moles of the weak acid. Then we can work out our Ka. So Ka is equal to 10 to the minus pKa, which equals 10 to the minus 5.12, which is equal to 7.59 times 10 to the minus 6 to 3 significant figures. So that's the extra step here that we didn't have to do in this first example. So that will get us an extra mark here. But at this point, we've now got everything that we need to be able to, again, write our Ka expression. Now, because they've given us it as HX and NaX, I'm going to follow suit and go with H plus and X minus as opposed to A minus, but they mean exactly the same thing, so don't be thrown by that. And then dividing it by HX. And then again, when I rearrange it to get H plus as the subject, this is where I would then drop the square bracket. So Ka times the moles of HX divided by the moles of the X minus. Now we can just sub the numbers in to that rearranged Ka expression. So Ka we just worked out as 7.59 times 10 to the minus 6. And then I'm going to be timesing that by the moles of the weak acid, which is 0.00306. And then I'm going to be dividing that by the moles of the salt of the weak acid, 0.02085. That's then going to give me a value for the H plus concentration, which I'll just need to work out. So bear with me a second. Which gets me 1.11 times 10 to the minus 6 to 3 significant figures. And then from there, pH is equal to minus log base 10 of the H plus concentration. So thus pH is equal to, my apologies, 5.95, remember, to 2 decimal places. So Hopefully you can see that the methodology for those two questions is the same, just an additional step is required in that second example to work out our value for Ka. We also needed to work out the moles of the salt of the weak acid, but that was using the same moles as concentration times volume method that we'd used in the first example. I've laid out everything exactly the same way, and that is exactly how I would come to lay it out in an exam question. Hopefully seeing that has been useful, and you can see how I've worked out each of the pieces of information needed to then follow that set of steps there in order to get the pH of these particular buffer solutions. So now we just need to have a look at the second way we can prepare an acidic buffer. So we've been looking at adding the salt of the weak acid to the weak acid in the same vessel. In method 2, we're going to add an alkali to an excess of the weak acid to make the salt in situ. So that means that all the alkali will get neutralised by some of the weak acid, which will generate a certain amount of salt, and then will leave us with enough weak acid left at the end to leave us with that buffer solution where we have the salt and the weak acid together. There can be no alkali left at the end here, and we have to make sure we have weak acid left at the end. So let's have a look at the final example for this video, and hopefully again you'll be able to see how I lay all of this out, where I get my information from in the question, and then you can apply this yourselves to other examples. So in this question, 100 centimetres cubed of 0.0515 mole per decimetre cubed of nitrous acid was mixed with 50 centimetres cubed of 0.0428 moles per decimetre cubed of sodium hydroxide solution. The Ka for nitrous acid is 7.20 times 10 to the minus 4 moles per decimetre cubed at 25 degrees. Calculate the pH of the buffer solution. So, first thing I'm going to do is I'm just going to recognise that we've been given a value for Ka, so we're not going to have to use the relationship with pKa this time around, so that's very kind of them. Then we've got information about the weak acid, which is the nitrous acid. 100 centimetres cubed of this, and the concentration of that nitrous acid solution is 0.0515. And then, of course, we haven't been given any information about the salt because we're going to make that in the reaction of the nitrous acid with the alkali that we're adding. So I'm going to use purple for my alkali. So we're using 50 centimetres cubed of a 0.0428 moles per decimetre cubed solution of sodium hydroxide. So that's my alkali. Now, the first thing we have to always do in these kind of situations is write a balanced chemical equation. And then from there, we'll be able to work out the moles of the weak acid we have, the moles of the alkali that we have, and see how they're going to react together to make the salt. So, nitrous acid is HNO2. And we're going to react that with sodium hydroxide, which is NaOH. And then when we make a salt, it's the hydrogen from the acid that gets replaced by the sodium in this case, or the metal from the alkali. So the salt is going to be sodium, I want to say sodium nitrate with a particular oxidation state, which would be +4. But the name of that is irrelevant. That would be the salt of our weak acid. And then the other thing we always make in neutralisation is water. And that's my starting point. Now, they're going to react the weak acid and the alkali in a 1-to-1 ratio, which makes this part of the calculation a little bit nicer. Heaven forbid it wasn't a 1-to-1 relationship, that when it came to working out how many moles had reacted and how much of the weak acid was left over at the end, you just have to take care and make sure you use the mole ratio correctly. Because it's 1-to-1, it's going to be a bit nicer here. But in all fairness, I think every single example I've ever done of this has been the weak acid and the alkali reacting in a 1-to-1 ratio. So let's hope that always stays the same. So then I'm going to work out the moles of the HNO2 by using the volume and the concentration. So the concentration of 0.0515 and the volume in decimeters cubed of 0.1 will give me moles of my weak acid of 0.00515 because I've done concentration times volume. For my alkali, which has to all get used up, the concentration is 0.0428 and the volume is 0.05. And if I work out what the moles of that is, by doing concentration times volume, I get 0.00214. Now, hopefully we can see that because these react in a 1-to-1 ratio, the HNO2, the weak acid, is definitely in excess because that is the bigger number. So what that means is all of my alkali is going to react with some of the weak acid. And the key thing is that's going to leave me with no alkali at the end, which is great because we can't have any alkali left at the end if we're trying to make a buffer solution. And I'm going to lose that many moles of my weak acid because that's how many moles of the weak acid would be needed to fully react with that moles of sodium hydroxide. And then I can work out what that is. Which is 0.00301. And then in terms of how much salt is made, again, the amount of salt made is also in a 1-to-1 ratio with the moles of weak acid and the moles of the sodium hydroxide. So that means we are going to make 0.00214 moles of salt. And we had no salt at the beginning because that's one of the products of the reaction. So that means that at the end, we're going to have 0.00214 moles of my salt. We're not interested in the water, so yes, we'd make that amount of water as well, but to be a buffer solution, we need there to be weak acid and we need there to be salt. And we've now got the moles of the weak acid that was left over, and we've now got the moles of the salt of the weak acid. So now we're at the stage where we were for the previous calculations when we'd worked out the moles of each of those two things in step 1. We've now got the moles of the weak acid, the moles of the salt of the weak acid, and we have a value for Ka. So now we can write our Ka expression and carry on as we were previously. So Ka is equal to H plus concentration times concentration of A minus divided by the concentration of the weak acid, Ha. When I now rearrange that to get the concentration of H plus equals, I'm going to drop the square brackets because we're going to use the moles of the weak acid and we're going to use the moles of the salt. So the H plus concentration is equal to the value for Ka, which we were given in the question as 7.20 times 10 to the minus 4 for the nitrous acid, and I'm going to be timesing that by the moles of the weak acid, which is 0.00301, and then I'm going to be dividing that by the moles of the salt, which is 0.00214. So now I just need to work out what that is. So again, just bear with me 1 second. That gets me a H plus concentration of 1.01 times 10 to the minus 3 moles per decimetre cubed to 3 significant figures. And then finally, pH will be equal to minus log base 10 of the H plus concentration, which we've just worked out, and thus pH to 2 decimal places is 2.99. So even in that method, everything from writing the Ka expression, rearranging it, subbing in the numbers, getting the pH is exactly the same. The only difference is how we have to find out the moles of the weak acid that we have and the moles of the salt that we have. So we have to work out how much alkali we're adding, make sure all the alkali reacts away, work out how much of the weak acid is reacted away during that neutralization to work out how much is left over at the end, and the amount of alkali that gets used up will be the amount of salt that is made. When you have those moles, the question becomes the same. Now, I really hope that you can have a look through those 3 examples and you can follow along with what I've done. Of course, if anybody has any questions, please feel free to comment on the video. Please feel free to drop me an email. The link will be in the caption. Please feel free to reach out on any of my social media channels and I will very happily explain certain steps of these calculations or help you to work through a different question where you are applying these methodologies. But if you watch this, maybe take a screenshot of it, then I'm sure you will be able to apply what I've done here to your own questions. I wish you all the very best of luck, and remember, part 2, which will be looking at the part 2 of these sorts of exam questions, will be coming next week, and in that video we'll be having a look at, now we have prepared our acidic buffer solution, what happens when we add a small amount of acid or alkali to that buffer solution. Thank you as always for watching. If you have any questions, like I say, please reach out. Hope you have a really good rest of your day and rest of your week. Thank you, everyone.